Tonight's journey moves in close calm detail through living galaxies, spirals traced with dust lanes and soft blue knots, ellipticals shaped like quiet domes of starlight, star formation rising, fading and leaving gentle patterns behind. This is Space Dreams Documentary, a slow immersive documentary to rest the mind while the universe keeps evolving. If this kind of deep, peaceful space storytelling belongs in your nights, please like the video and subscribe to Space Dreams Documentary for more long-form cosmic journeys released regularly. Now let the light soften, let the shapes drift, and let the story of galaxies unfold. A galaxy can look calm and still be busy. In a spiral galaxy, the bright arms usually mark where new stars form more often than elsewhere. A wide disk hangs in darkness. A central bulge glows with dense blended starlight. Around it, faint arms curve outward in a loose pattern. The arms do not look like solid bands. They look like regions of slightly higher brightness traced by soft patches and thin shadows. At this distance, the first contrast appears as a contrast of texture. Smooth light suggests settled starlight. Streaked light suggests gas dust and change. The disk turns slowly. The sense of motion is not seen as a blur. It is sensed through shape. The arms lean forward like a pattern that has been gently twisted. One small fact holds the scene together. A single rotation of a Milky Way-like spiral takes about 200 million years. That span is like a long chain of winters and summers for an entire planet. In that long turn, the arms remain visible. Yet the material inside the disk keeps moving. The first quiet unlock sits there. Spiral arms can be where starbirth prefers to happen, even while stars drift through the pattern. The view drifts closer to one arm. Starlight brightens in clumps. Between clumps, darker lanes cut across the glow. These lanes have edges that look soft, not sharp. The darkness is not empty. It is dust. Dust is tiny solid grains mixed into gas. It blocks and scatters light. It leaves a boundary that looks like smoke, but it is colder and heavier. Along the lane, the brightness drops in a gradient. The lane is darkest on one side. It fades on the other. That gentle gradient hints at thickness. It also hints at depth. An object would see a different galaxy if dust were absent. Light behaves as a filter here. Some colours pass through more easily. Some are muted. The arm becomes a layered place. One layer is old starlight. Another layer is gas and dust. Another layer is newborn stars that burn hot and bright. A second quiet unlock appears. The same spiral can seem calm in one band of light and restless in another because dust decides what escapes. The drift slows near a bright knot on the inner edge of the arm. The knot is not a single point. It is a region with a soft core and a faint halo. The halo blends into the surrounding disk like mist. At the knot's edge, the light looks grainy. That graininess comes from many small sources blended together. This is where the first core concept settles into plain language. Star formation rate is the pace of new stars appearing. It is not counted one by one. It is inferred from the kind of light that young stars tend to produce. It is also inferred from the glow of gas that becomes energized nearby. The pace rises where gas becomes denser. The pace falls where gas spreads thin. The disk becomes a map of uneven activity. In that region, a spiral arm behaves like a moving zone of mild compression. Gas enters. Gas slows a little. Gas piles up into filaments. Dust follows the gas into the same ridges. The scene resembles a natural pattern. It resembles the spiraling rose in a sunflower head. Seeds do not move through the pattern as a single piece. Yet the pattern holds and guides where packing becomes tight. In the galaxy, the packing is gas and dust. The tightening is gravity and pressure. The result is a place where new stars appear more often. Another slow visual anchor appears along the arm. A thin dust lane splits into smaller threads. The threads braid and separate. The threads curve like hairline cracks in dry mud. They trace a boundary between slightly different densities. At the boundary, the gas can cool more efficiently, Cooler gas can clump. Clumps can collapse. Collapse does not happen everywhere. It happens where the density crosses a threshold. The arm is not a rigid structure that forces collapse. It is a preference zone. It is an invitation in slow motion. The disk's rotation stretches the invitation into a long arc. A small payoff lands gently. Spirals do not need to be filled with constant fireworks. A modest rise in density is enough to tilt the odds towards starbirth. The scale shifts outward. Farther from the centre, the arm looks thinner. The bulge fades behind. The disk becomes more transparent. The brightness becomes more sparse. Here the arm still curves, yet the knots are fewer and dimmer. Gas is still present, but it is less compressed. The same pattern can mean different things at different radii. In the inner disk, a mild squeeze produces many bright nurseries. In the outer disk, the squeeze is weaker. Starbirth slows. That change carries a quiet lesson. A spiral shape alone does not guarantee high star formation. The supply and state of gas matter. The amount of cold gas matters. Cold gas is gas cool enough to clump into dense clouds. It is not cold by everyday standards. It is cold by interstellar standards. In a disk, cold gas often sits in a thin layer near the midplane. It forms sheets and filaments. It forms pockets that can collapse. The arm crosses that layer like a gentle ripple passing through shallow water. The ripple does not create the water. It gathers the water into lines. Another visual anchor settles into place. The disk is seen edge on for a moment. The starlight forms a thin, bright band. A darker stripe lies along the middle. That stripe is the dust lane seen from the side. It looks like a seam. It looks like a soft shadow pressed into the disk's brightest line. The thickness of the stripe changes with radius. The stripe becomes thinner outward. That thickness is a physical detail. It hints at where dust concentrates. It also hints at how the disk is layered. The arm is now understood as a pattern tied to a thin, dusty, gas-rich plane. The pattern is broad. The material is confined. A small payoff arrives without fanfare. The most visible spiral features often live in a thin layer even while the galaxy as a whole has depth. Now a limit of intuition appears softly and specifically. Star formation rate is not seen directly. It is inferred from light and from the glow of surrounding gas. Dust can hide the brightest newborn regions. It can also mimic age by dimming and reddening light. In addition, distance blurs detail. Many separate clouds can merge into one unresolved patch. A signal would carry only what escapes from the region. That makes interpretation uncertain. Two galaxies can share the same spiral shape. One can be dustier, one can be clearer. The same measurement can suggest different star formation rates depending on what is hidden. The spiral arms also play a trick of geometry. An arm seen face-on looks like a line of knots. The same arm seen at a tilt looks smoother. Depth piles light on top of light. That limit matters because early conclusions can be false calm. A quiet arm can still host busy starbirth behind a veil. The view returns to the face on disk. The arm is followed across a gentle curve. Bright knots appear at intervals. Between them the dust lane widens. Then it narrows. The lane's edge becomes ragged. The raggedness suggests turbulence. Gas is not still. It moves in eddies and streams. The arm's compression guides these motions. It turns loose flow into organized ridges. The ridge is not permanent in the same material. It is persistent as a pattern. Another payoff settles in. The arms are both structure and process. They are shape, and also a schedule for where gas becomes dense next. The disk turns on, the arm passes, the gas enters, the gas leaves. Starbirth leaves behind clusters and associations that drift onward. Over long time those young stars age. Their light softens. Their imprint fades into the background of the disk. The scene widens again. The galaxy becomes a single luminous form. The bulge is warm and smooth. The disk is wide and faint. The arms are the gentle handwriting across it. In that handwriting, the first promise of the journey is set. Spirals and ellipticals can be compared through two calm questions. How much cold gas remains? How often new stars appear? The next step moves from the spiral's active lanes toward the smoother glow of an elliptical form, where the texture changes and the pace of birth often quiets. A galaxy can glow without showing any lanes or arms. An elliptical galaxy often looks smooth because its gas is scarce, and its stars move in many directions. At this distance, the light forms an oval haze. The center is brightest. The brightness falls outward in a slow gradient. No spiral handwriting crosses the disk because there is no disk. The outer edge has no sharp boundary. It fades into darkness like powder brushed thin. A slow drift across the center shows a quiet symmetry. The glow looks like it is poured into space and left to settle. The first small unlock arrives early. Smoothness is not emptiness. Smoothness is many overlapping orbits blended into one calm shape. Closer in the center shows a subtle change. The core is denser. The light there is warmer and more uniform. Away from the core, the texture becomes faintly grainy. That grain comes from countless older stars whose light overlaps. The physical detail sits in the profile itself. The inner region rises steeply. The outer region declines gently. That curve matters because it hints at structure without needing visible arms. In that region, stars do not mostly circle in one flat plane. Their paths tilt and cross at many angles. The light becomes like a thick fog of points seen from far away. An everyday analogy holds the scene. It resembles a jar filled with fine sand that has been shaken. The grains settle into a rounded mound. No single grain draws a line, yet the mound has a stable shape. In the same way, an elliptical galaxy is a stable pile of orbits. The second small unlock appears. A spiral galaxy shows order through rotation. An elliptical shows order through balance. The view moves outward until the galaxy nearly fits the frame. The oval becomes more obvious. The outer glow is faint. It is not featureless if the exposure were deep enough. Subtle shells can exist. Faint ripples can exist. These are not common in every elliptical. When present, they look like thin arcs embedded in the halo. They suggest an old disturbance that has spread out. The arcs have a boundary that is soft like a shoreline seen through mist. They are not bright enough to dominate the shape. They whisper that the smooth form can still carry history. The section holds to three core ideas. The first is orbit mixing. The second is gas poverty. The third is star formation quiet. Orbit mixing means stellar paths point many directions. This mixing smears structure. It makes arms hard to keep. Gas poverty means little cold material remains to clump. With little cold gas, new stars form rarely. A simple number anchors the difference in pace. In many ellipticals, the time since most stars formed is about 10 billion years. That span is like the time it takes for mountains to rise and wear down many times over on a planet. Such a long age does not mean nothing changes now. It means the main building phase lies far behind. The light carries that age as a gentle colour shift. Older stars tend to look redder. Younger stars tend to look bluer. In a smooth glow, the red tone can dominate. A slow visual anchor arrives near the outskirts. The halo is dim and wide. It stretches farther than the bright centre suggests. The halo's edge fades in a long gradient. No border marks where the galaxy ends. Only the background grows darker. This gradual fade is a physical clue. It reflects how stars are distributed across large distances. The scale shift is calm. From a bright core smaller than a small moon in the frame, the view expands to a halo spanning many tens of thousands of light years. The galaxy becomes a quiet island of light in a larger ocean of darkness. The next unlock settles in. Without a thin disk, gas has less reason to stay confined. When gas is heated, it becomes harder to cool. When it cannot cool, it cannot sink into dense clouds. Dense clouds are the usual cradles for new stars. In ellipticals, much gas is hot and thin. Hot gas is not hot like flame. It is hot enough that its atoms move fast and resist collapse. It fills the space between stars like a faint atmosphere. Light behaves as a clue here. Hot gas can glow in bands of radiation that are not seen by human eyes. That means the gas can exist and still look invisible in ordinary light. The smoothness in visible light can hide a different structure in other bands. That leads into a limit of observation stated gently and clearly. Measurements of star formation in ellipticals are hard because the usual bright signs are weak. Dust lanes are rare. Bright young clusters are scarce. Signals can be buried in the combined light of old stars. In addition, distance blurs faint edges into the background. Small pockets of new stars can vanish into the core's glare. A model may also assume a certain mix of stellar ages. If that assumption is off, the inferred star formation rate can be misleading. The limit is not ignorance, it is blending, it is low contrast. It is the difficulty of separating faint new light from strong old light. Another slow scene returns to the core. The brightest region appears almost smooth as glass. Yet it is not a single surface. It is a layered depth of countless stars at different distances. The center's brightness falls outward in a rounded gradient. That gradient is the footprint of gravity holding the system together. The stars move in many directions. Their speeds are high. The motion is not seen directly. It is felt in the stability of the shape. An everyday analogy makes the motion easier to imagine. It resembles a swarm of drifting dust motes in a sunbeam. Each mote moves in its own path. From far away the beam looks steady. The beam's steadiness is not stillness. It is averaging. A small payoff lands. Ellipticals look calm because their motions cancel into a smooth glow, not because motion is absent. The gaze pulls back again. The elliptical sits alone, an oval ember in the dark. The absence of arms becomes meaningful. It suggests the absence of a thin rotating disk rich in cold gas. It suggests a history where gas is used up heated or removed. It suggests orbits are scrambled and mixed. This does not make ellipticals simple. It makes them quiet in one kind of light. In that quiet, the next step becomes clear. The comparison between spirals and ellipticals sharpens when the pace of new stars is measured and when gas supply is traced. The next section moves toward the calm yardstick itself and how it reveals hidden activity. Some galaxies hide their freshest light in the faintest corners. Star formation rate becomes the calm measure of how quickly new stars appear, even when the scene looks quiet. At this distance, a spiral arm and an elliptical core can be compared without forcing them into the same shape. The comparison begins with a simple idea. Young massive stars change the light of a galaxy more than their numbers suggest. They shine intensely. They live briefly. Their presence acts like a fresh scent in a large room. It does not last long. It signals recent activity. The first small unlock arrives. Star formation rate is not about how many stars exist. It is about how recently new ones have joined the mix. The view drifts toward a spiral arm first. The arm is not a line. It is a loose band of slightly higher brightness. Dust lanes cross it as soft shadows. Between the shadows, pale knots glow. Around some knots, a faint haze spreads outward. That haze can come from gas affected by nearby young stars. The physical detail is in the edge of the haze. It fades with a smooth gradient. It does not stop sharply. Light behaves as a clue here. When very young stars appear, their energetic light can excite surrounding gas. The gas then glows in characteristic colours. In visible light, that glow can look like a soft tint. In other bands, it can be more obvious. This is where the measurement begins. A galaxy's star formation rate is inferred from these signs. It is inferred from light that favours youth. It is inferred from gas glow that favours recent birth. The scene shifts inward to a quieter part of the same galaxy. The disk there is smoother. The knots are fewer. The dust lane still exists, but it thins. The arm's pattern remains. Yet the youthful light fades. Another small unlock settles in. A spiral can carry arms and still have low star formation in places. The pattern is not a guarantee. It is a stage. The play depends on gas. Now a different anchor appears. A wide field of starlight looks warm and uniform. The background glow dominates. This is the light of older stars. In that field, a small blue patch can matter more than its size suggests. It can be the signature of a recent burst. It can also be the signature of low dust. The difference is subtle. It requires care. An everyday analogy holds the uncertainty gently. It resembles judging the heat of a stove by the smell in the air. A sharp smell suggests recent cooking. Yet open windows can change the smell without changing the stove. In the same way, dust and geometry can change the light without changing the true pace of starbirth. A slow, visual anchor arrives as a thin, translucent veil crossing the arm. The veil has a darker ridge. The ridge casts a soft shadow. The shadow widens as it crosses a brighter region. That widening suggests thickness. It suggests layered dust. In that region, the youthful light is partly hidden. The measured star formation rate would appear lower than it truly is. A second unlock arrives. Dust does not just dim light. Dust reshapes the story that light can tell. The scale shift becomes calm and wide. A single glowing knot can span a few tens of light years. The whole galaxy spans tens of thousands of light years. The same physics that governs a cloud also shapes the global rate when many clouds add together. The drift pulls back to show the spiral as a whole again. The arms are now a pattern across a disk. The bright bulge sits at the centre. The disk is faint at the edges. The youthful signs appear as scattered accents, not as a uniform wash. The rate is patchy in space. It is also variable in time. Star formation can rise and fall over tens of millions of years. That span is like a slow tide compared with the brief lives of the brightest young stars. A single number anchors the idea of briefness. A typical massive bright blue star lives about 10 million years. That span is like a single long chapter in the history of a mountain range. It is short compared with a galaxy's age. This matters because the measurement is sensitive to the recent past. If the bright young stars fade, the signal fades quickly. Another visual anchor settles in. A ring of faint glow surrounds a brighter patch. The ring is not perfectly circular. It is slightly warped. It looks like a thin ripple. The ripple can mark a region where gas has been compressed in a wave. Such compression can trigger starbirth. Yet the ring is faint. It suggests the trigger is mild or old. The small payoff arrives. Star formation rate is a moving snapshot. It highlights recent changes, not the whole long history. Now the focus shifts to an elliptical galaxy. The light is smoother. The centre is bright. The gradient outward is gentle. No dust lane cuts the middle. No bright knots appear in the same way. That does not mean the rate is exactly zero. It means the obvious signs are weak. The measurement becomes harder. It must detect faint youth against strong age. It must separate the small signal from the dominant background. This leads into a clear limit of observation. In ellipticals, young stars can be hidden by blending. Their light can be overwhelmed by older stars. In addition, low levels of star formation can fall below detection in ordinary light. The inference depends on models of stellar populations. Those models assume how many stars of each age exist. If that assumption is wrong, the inferred rate shifts. Resolution also matters. At large distances, small star-forming pockets merge into the central glow. A signal would arrive as a single smooth haze. The pockets vanish into it. The limit is contrast. The limit is blending. The limit is reliance on indirect interpretation. Another slow scene returns to the spiral, and then to the elliptical like a gentle comparison without sharp judgment. In the spiral, dust lanes carve shadows. In the elliptical, shadows are rare. In the spiral, scattered youthful accents appear. In the elliptical, the light is steady and warm. The everyday analogy shifts to a new image. It resembles a garden seen at dusk. In one garden, small new sprouts catch the last light as bright specks. In the other garden, only mature leaves form a uniform canopy. The canopy can still be healthy. It simply shows fewer fresh tips. Another small unlock arrives. Star formation rate separates appearance from activity. It can reveal a quiet spiral that is running low on gas. It can reveal an elliptical that has a faint trickle of new stars in one region. The view pulls back to a wider scale again. Many galaxies would fill a large volume. Some would be blue-tinted and clumpy. Some would be red-tinted and smooth. The distribution of star formation rate across these types becomes a map of evolution. The next step moves toward the fuel itself. Cold gas decides what the rate can become. The next section shifts into the reservoirs and the ways gas gathers, cools, and sometimes disappears. Some galaxies keep their future hidden in a thin, dim layer. Cold gas is the quiet reservoir that decides whether new stars can still appear. At this distance, the reservoir is not seen as a single pool. It appears as texture, shadow, and faint glow arranged across a disk. The first view is edge-on. A bright band of starlight stretches across the frame. Through its middle runs a darker seam. The seam is not sharp. It has a soft boundary and a thickness that changes with radius. The seam is dust mixed into gas. It blocks light and leaves a shadow line. The physical detail is in the gradient of that shadow. It is deepest at the midplane. It fades upward into the halo. A small unlock arrives early. The fuel for star formation often lives in a thin layer even when the galaxy looks thick and calm overall. The drift turns the galaxy face on again. The disk becomes a wide plate of light. Across its dark lanes curl and split. The lanes are uneven. They thicken in some places. They fray into threads in others. Between lanes, the starlight is brighter. The lanes trace where gas gathers. Gas and dust move together because dust is carried by gas. In that region, cold gas means gas cool enough to clump into dense clouds. It is not cold like winter air. It is cold compared with the surrounding hot, thin medium. This is the first core concept. The second is shielding. Dust helps gas stay cool by blocking harsh light. The third is collapse. Dense pockets can fall inward under gravity and begin starbirth. The scene follows a single lane. Its edge looks scalloped like a torn ribbon. The scallops mark density variations. Where the lane thickens, the background light dims more strongly. That dimming indicates more material along the line of sight. Light behaves as a soft probe. Where light is missing, material is present, yet absence can lie. A lane can look dark because it is thick. It can also look dark because it lies in front of a bright region. Geometry matters. The lane leads to a brighter knot. Around the knot is a faint haze that fades outward. The haze suggests nearby young stars, but the knot itself can be the cloud before or after starbirth. Another visual anchor appears. A set of parallel filaments runs beside the main lane like comb marks. Filaments imply a flow. Gas can stream along spiral patterns. It can gather in ridges. It can fragment into strands. The everyday analogy for the whole process is gentle and simple. It resembles dough being folded again and again. Each fold creates layers. Each layer traps pockets of air. In the galaxy, folds are waves and shear. Layers are gas sheets. Pockets become clouds. Another small unlock arrives. Cold gas is not just a quantity. It is a structure that must be kept intact against mixing and heating. The drift shifts scale. It moves from a filament tens of light years long to the full arm spanning thousands of light years. The same lane that looks like a single stroke up close becomes a network at larger scale. The network is the reservoir in a usable form. Without the network, gas is too diffuse. It cannot collapse easily. The disk rotates. The lanes curve with it. The curvature implies motion. It implies the gas is not static. It circulates, collides, and reshapes itself. In that region, shielding becomes crucial. When dust blocks energetic light, the interior of a cloud cools more effectively. Cooler gas has lower pressure. Lower pressure allows gravity to win more often. A small payoff settles. Dust lanes are not only obstacles to vision, they are often the outlines of future star-forming sites. A single number anchors the scale of that thin layer. The cold gas layer in a spiral disk can be about 100 light-years thick. That thickness is like stacking 100 trillion Earth orbits across a single vertical slice then still calling it thin. The comparison is not about exactness. It is about perspective. 100 light-years is slender next to a galaxy's width, yet it is vast next to a single cloud. The layer is thin in a galactic sense. It is deep in a local sense. Another visual anchor arrives as the view slides along the midplane. The dust seam becomes slightly warped. It bends upward on one side. It dips on the other. The warp is subtle. It looks like a sheet that has been gently lifted. That warp hints at disturbances. Passing structures and uneven gravity can tilt the gas layer. The warp changes where gas settles. It also changes where lanes appear darkest. Another small unlock appears. Even a calm disk can carry gentle bends that rearrange the reservoir over long time. Now the limit of observation enters clearly. Cold gas is often traced indirectly. Much of it does not shine brightly in visible light. It can be inferred through dust, but dust is only a partial proxy. Dust to gas ratios vary. Geometry varies. In addition, the densest parts can be hidden behind the darkest lanes. When a region is too opaque, the interior becomes invisible in ordinary light. Resolution also matters. At large distance, many small clouds blend into one smooth shadow. A model may interpret it as one structure. In reality, it can be many. The limit is not only sensitivity, it is also confusion along the line of sight. A signal would mix near and far material into one silhouette. That makes the true three-dimensional shape uncertain. The view returns to a quieter part of the disk. Here the dust lanes thin, the starlight brightens and smooths. This is not necessarily a healthier region. It can be a region where the reservoir is depleted. It can be a region where gas is heated and spread out. The absence of lanes can mean less fuel. Another payoff lands. In galaxies, darkness can mark abundance, and brightness can mark scarcity depending on what is being traced. The drift pulls back. The spiral arms remain visible. The reservoir is seen as the lacework of lanes across the disk. In an elliptical, such lacework is usually missing. That missing lacework hints at a different gas state. Gas can exist but be hot and diffuse. It does not settle into a thin, cold layer. Without that layer, collapse becomes rare. The story now has a steady hinge. The star formation rate follows the reservoir. The reservoir follows how gas cools, how it is shielded, and how it is gathered. The next step moves toward the motions that gather gas, especially the way rotation and shear shape spirals into long-lived patterns that guide the reservoir without freezing it in place. A spiral pattern can stay visible even while its stars keep moving on. Rotation and shear shape spiral arms as long-lived zones, not fixed bands of matter. At this distance, the disk looks like a faint wheel of light with curved strokes laid across it. The center glows softly. The outer disk is thinner and darker. The arms do not have hard edges. Their brightness rises and falls in a gentle gradient. Dark lanes trace along the inner side of some arms. Those lanes bend with the curve. The physical detail sits in their offset. The darkest dust often lies slightly ahead or behind the brightest knots depending on the arm's geometry. That offset matters because it hints at flow. It hints that gas enters the arm region, compresses, and then leaves it. A first small unlock arrives early. Spiral arms can be traffic zones. The pattern stays while the travellers change. The scene drifts closer to one arm. The arm is not smooth. It is stitched with scattered clumps. Between clumps, the background light is faint. Along one side, a dust lane looks like a soft seam pressed into the glow. The seam splits into threads. Threads merge again. The seam is a map of density. In that region, rotation means material circles the centre in an orderly sense. Shear means inner parts circle faster than outer parts. The inner disk completes a loop more quickly. The outer disk lags behind. This difference stretches features. It turns short patches into long curves. The everyday analogy for shear is simple. It resembles a brush dragged across wet paint. The top of the paint moves faster than the bottom. The streak becomes a curve. The curve can persist even as the paint itself mixes. Another small unlock settles. Shear can create spirals from gentle disturbances. It can also keep them from collapsing into one clump. The view shifts outward along the same arm. The curvature changes. The arm opens up. The spacing between clumps becomes larger. The dust lane thins. This is a scale shift inside one structure. The inner region feels dense and busy. The outer region feels airy and quiet. The same arm carries both feelings. A slow visual anchor appears where the arm crosses a faint ring-like arc. The arc is not a perfect ring. It is a partial curve like a pale ripple trapped in the disc. Along the ripple, the brightness is slightly higher. The ripple has a leading edge where the gradient rises more steeply. That steepness suggests a mild compression wave. The wave is not a wall. It is a region where gas is nudged into denser lanes. That nudge is enough to tilt the odds toward cloud formation. Another small payoff arrives. Spiral structure can be a gentle organizer. It does not need to be a violent shaper. Now a new term appears and is kept brief. A density wave is a moving pattern of higher density. It is not a fixed set of stars. It is a pattern that material passes through. The example is the arm itself. Gas streams into the arm region. Gas slows slightly and piles up. Then it flows onward. The why is quiet and useful. A pattern like this can keep spiral arms visible for long spans. It also helps explain why star formation clusters along the arms. The camera drifts along the arm as if following the flow. The dust seam grows darker. Then it fades. Bright knots appear after the darkest parts. The sequence implies timing. First gas compresses and dust thickens. Later young stars brighten nearby regions. The arm becomes a soft timeline drawn in light and shadow. Another visual anchor arrives in the interarm space. The light there is not empty. It contains faint stars and thin haze. A few isolated clumps sit away from the main arm. Their edges are soft. Their halos fade outward. They suggest clouds that have drifted out of the main ridge, or small regions triggered by local compression. This is another quiet unlock. Star formation is not locked inside the arm. The arm is a preference, not a cage. The scale shift widens further. The view pulls back from one arm to the full disc. The arms now appear as a set of curves that wind outward. Their pitch changes with radius. Some segments look tighter, some look looser. The pattern is not perfectly symmetric. This asymmetry is important. It suggests that spiral structure can be influenced by small imbalances and by the distribution of mass. A spiral is a living map of a disk's internal motion even when the disk looks calm. A single number anchors how shear builds curves over time. A typical spiral can complete a rotation in about 200 million years. That span is like the time it takes for a coastline to be reshaped many times by slow waves. In that long rotation, shear keeps stretching features. It also keeps renewing the curve of the pattern. Yet the number is not a clock for the arm itself. The arm can persist longer than a single orbit as a pattern. This is the next small payoff. The arm is not a painted stripe on the disc. It is more like a standing ripple in a rotating medium. The everyday analogy shifts to a new image and stays unique. It resembles a long scarf being gently twisted while it is pulled forward. The twist pattern remains visible. The fibers within the scarf keep sliding past one another. The twist is the spiral pattern. The fibers are the stars and gas. Now, a limit of intuition and observation enters clearly. It is tempting to treat arms as solid objects. In images, arms look like material structures. In reality, a single star's motion is hard to track. Distance hides proper motion. Images compress depth into a flat view. In addition, different wavelengths highlight different components. Dust young stars and old stars can trace slightly different arm shapes. That makes it hard to define the arm's exact boundary. Models also simplify. Some assume steady patterns, some assume transient patterns. Both can fit limited data. The limit is not just resolution, it is also projection. A signal would carry only the integrated light along the line of sight. That blending can disguise whether an arm is a long-lived wave or a short-lived feature. Another slow scene returns to the dust seam at close range. The seam curves like a soft shadow line. It thickens into a darker knot. Then it breaks into threads. The threads drift into the background glow. This scene holds the mechanism in a calm way. Shear stretches, compression gathers, gravity clumps, then rotation carries the result onward. Another small payoff settles. Spiral structure is a choreography of gentle forces, not a single cause. The section closes with a soft transition. The next step moves inward toward a different organizer, a bar-shaped structure that can channel gas and reshape the center. The disk remains calm. The focus simply shifts from curved arms to straightened flow near the core. A spiral galaxy can carry a straight feature inside its curved arms. A central bar often guides gas inward and reshapes the inner disk over time. At this distance, the galaxy is face-on. The outer arms curve gently. Near the center, the light stretches into an elongated oval. The oval crosses the core like a faint beam. Its ends blend into the inner spiral pattern. The physical detail is in the bar's edges. They are not crisp. They fade into the surrounding glow with a shallow gradient. Along the bar, thin dust streaks appear. They run parallel for a while. Then they bend inward near the center. That bend hints at flow. A first small unlock arrives early. A bar is not only a shape, it is a pathway that can move the cold gas reservoir toward the core. The view drifts closer to the bar. The bulge is brighter now. The bar's surface is mottled. Small brightness knots sit along its length. Between knots, dim lanes create soft shadows. Those shadows look like shallow grooves pressed into the light. In that region, gravity is not perfectly symmetric. The bar is an elongated mass distribution. It can apply gentle torques to gas. Torque is a twist that changes motion. Gas responds more than stars because gas can collide and lose energy. Stars pass through. Gas shocks and compresses. This is the first core concept. The second is inflow, the gradual movement of gas towards smaller radii. The third is central build-up, where inflow can feed star formation in the inner region. An everyday analogy holds the idea without urgency. It resembles rainwater sliding along shallow channels in a sloped garden. The channels do not create the water, they guide where the water pools. In the galaxy, the channels are dust lanes along the bar. The pooling is gas gathering near the center. Another slow visual anchor appears. Two dark dust lanes run along the leading side of the bar. They are slightly offset from the brightest ridge. Their offset is a physical clue. It suggests the gas is compressed at a boundary as it streams along. The lanes narrow in some places. They widen in others. At their widest points, the background starlight dims more deeply. That deeper dimming suggests higher column density. Another small payoff settles. A bar can turn a broad scattered reservoir into a more concentrated one. Concentration raises the chance of dense clouds. Dense clouds raise the chance of new stars. The view follows one dust lane inward. The lane curves toward the core. Near the center, the lane becomes tangled. It splits into smaller filaments. The filaments form a loose ring-like arc around the nucleus. The arc is not perfectly circular. It is an oval loop that mirrors the bar's orientation. The inner region looks layered. A bright central glow sits inside. Around it sits the faint ring. Outside it sits the bar's elongated light. These layers make a quiet map of flow. Gas can stream inward along the bar. Then it can stall at certain radii. There it can form a ring of higher density. Within that ring, star formation can rise. The next small unlock arrives. Bars do not always feed the very center directly. They can also build rings that become inner nurseries. The scale shift becomes gentle and clear. The dust lane seen at close range can be tens of light years wide. The bar itself can span several thousand light years. The whole galaxy spans tens of thousands. The same guiding effect is felt across these scales. A pattern in the inner few thousand light years can influence the global star formation distribution. It can move the action inward. It can thicken the inner disk by adding new stars there over time. One number anchors the pace of this slow rearrangement. A bar can persist for about 1 billion years. That span is like the time it takes for a continent to drift a noticeable distance across an ocean basin. During that long span, the bar keeps nudging gas. It keeps shaping where density gathers. The change is gradual. The bar's effect is more like steady pressure than a sudden push. Another visual anchor appears as the view tilts slightly. The bar's elongated glow becomes a subtle bulge in depth. The disk remains thin. The bar region looks thicker with a broader light profile above and below the plane. That thickness suggests heating of stellar orbits in the inner region. It also suggests that inflow and repeated star formation can build a more prominent central structure. Another small payoff lands. The bar can change a galaxy from the inside out, not by breaking it, but by slowly relocating fuel and building mass in the center. Now a limit of observation enters softly and specifically. Bars are easy to see in some orientations and hard to see in others. A bar seen end-on can look like a round bulge. Dust can also hide the inner shape. In addition, bright central light can wash out faint lanes. Measurements of inflow are indirect. They rely on mapping gas and inferring motion from subtle shifts in spectral lines. If resolution is coarse streaming motions blur into rotation, a model may assume a simple flow pattern. Real gas can follow multiple paths and fragment into clouds. The limit is geometry and resolution. The limit is that motion is inferred from light not watched directly. Light behaves as a partial messenger. It carries the combined signal of many layers along the line of sight. The scene returns to the ring like arc near the center. The arc's edge is brighter on one side. It fades on the other. The asymmetry suggests uneven gas density or uneven recent star formation. The arc is calm. It is not a flashing sign. It is a slow glow embedded in the inner disk. The everyday analogy shifts to a new unique image. It resembles grains of rice sliding down a shallow funnel. The grains do not move all at once. They collect and then trickle onward. In the galaxy, gas is the grains. The bar is the funnel shape that guides the drift. Another small unlock settles. A bar can regulate the central region by controlling how steadily fuel arrives. The view pulls back to include the outer arms again. The curved spirals and the straight bar coexist. The galaxy now reads like two patterns layered together. One pattern organizes the outer disk through rotation and shear. The other pattern organizes the inner disk through torque and inflow. The transition forward is gentle. The next section moves beyond internal reshaping and into close encounters. In crowded regions, tides can pull long streams and briefly raise star formation in places far from the core. Two galaxies can pass close enough to leave marks without touching in any simple way. Tidal forces stretch stars and gas into long streams, and those streams can briefly raise star formation in compressed pockets. At this distance, the first view is wide and quiet. Two luminous forms share the same dark field. One is a spiral with curved arms and dust seams. The other is a smaller companion with a smoother glow. Between them, faint haze forms a bridge. The bridge is thin. It is uneven. It has a brighter spine and softer edges. The physical detail is in the bridge's taper. It narrows toward the middle. It fades outward in a long gradient. That taper suggests material being drawn out and diluted. A first small unlock arrives early. Close passages can rearrange a galaxy's fuel without requiring a direct collision of disks. The scene drifts closer to the spiral's outer edge. One arm looks pulled longer than the others. Its curvature is distorted. The arm's outer tip becomes a ribbon. The ribbon arcs away from the disk. Along the ribbon, brightness comes in beads. The beads are spaced irregularly. They look like knots on a string. Between knots, the ribbon dims. The ribbon's edge is soft. It frays into faint threads. This is a tidal tail. It is made of stars and gas drawn outward by differential gravity. Differential gravity means one side is pulled more strongly than the other. The difference is small across a single star. It is large across a whole galaxy. The everyday analogy stays calm and unique. It resembles taffy being pulled slowly from a warm lump. The lump remains. A strand stretches out. The strand thins. Small, thicker parts remain along the strand. In the galaxy, gravity supplies the pull. The tail is the strand. The knots are places where gas becomes denser. Another slow visual anchor appears in the tail's beads. Each bead has a brighter core and a faint halo. The halo fades outward. The core sits inside a darker rim where dust can thicken. The rim makes a soft shadow. That shadow has a curved boundary that matches the bead's shape. The bead becomes a laboratory for compression. Tidal forces do not only stretch, they also squeeze in some regions. As gas streams along the tail, it can shock and cool. It can collect into clumps. Clumps can collapse. This is the first core concept. The second is tidal torque, the twist that changes gas motion and drives inflow or outflow. The third is triggered star formation, the rise in starbirth caused by compression. A small payoff settles. A tail is not only debris, it can become a temporary cradle for new stars in its densest knots. The scale shifts gently from one bead to the full tail. A single bead can be a few hundred light years across. The tail can extend tens of thousands of light years. That span is like a ribbon that could wrap around a galaxy's bright disk and still have length left over. The tail's length matters because it shows how far the pull can reach. It also shows how much material can be moved away from the disk. The view returns to the region between the two galaxies. The faint bridge thickens near the companion. Near that end, the bridge curves like a stream joining a pool. Along the curve, dust forms a narrow lane. The lane bends inward toward the companion's core. The lane is darker on the inner side. It fades on the outer side. This gradient suggests the lane has depth and a preferred direction. Gas is not simply floating, it is flowing. Light behaves as a tracer. Where dust blocks gas is likely concentrated. Another small unlock appears. Interactions can funnel gas into new places, sometimes into the center, sometimes into the outskirts, depending on the geometry. The drift moves to the spiral's inner region. The central bar and inner disk are now more disturbed. The bar looks slightly off-center. The inner dust lanes are twisted. A faint ring-like arc near the center brightens in patches. Those patches can be young star-forming regions fed by inflow. The encounter can stir the disk. It can create new compressions where gas piles up. It can also heat or scatter gas so it becomes harder to cool. The outcome depends on details. The distance of closest approach matters. The angle matters. The gas content matters. A calm number anchors the timescale of a close passage. The strongest tidal distortions can develop over about a few 100 million years. That span is like the time it takes for a forest to grow from seedlings to a mature canopy, then begin to thin again. In the galaxy, this is a brief episode compared with a long lifetime. Yet it is long enough to reshape structure. It is long enough to move gas across large distances. Another visual anchor appears in the spiral's outer disk. One side looks sharper. The brightness drops more quickly there. The opposite side looks smeared with faint light extending outward. This asymmetry is a physical clue. It suggests one side is being pulled and one side is being compressed. The compressed side can form more dense clouds. The pulled side can thin out and lose its ability to form stars. A small payoff lands. An interaction can both boost and suppress star formation at once in different parts of the same galaxy. Now a limit of observation enters softly and specifically. Tidal features are faint. They can be missed if the surface brightness is too low. Distance dims them further. Projection can also mislead. A tail seen end-on can look like a small knot. A bridge can overlap the disk and vanish in glare. In addition, the timing is uncertain. A single image is a snapshot. It does not show the full orbit. Models must infer the past path from present shapes. Different encounters can produce similar tails. That creates ambiguity. The limit is low contrast and the need for indirect reconstruction. A signal would carry only the combined light of many layers. The true three-dimensional shape is hidden. The scene returns to the tail's beads. Some beads glow slightly brighter than the surrounding ribbon. Their edges are not sharp. They fade into the tail's faint light. Within each bead, the densest gas can be hidden behind dust. Star formation can be active and still appear modest. Another small unlock settles. Triggered star formation is often localized. It can be intense in a few knots and quiet elsewhere, even during a dramatic-looking interaction. The view pulls back to include both galaxies again. The bridge remains faint. The tail remains long. The disks remain mostly intact. The encounter feels like a slow dance of gravity rather than a crash. The transition forward is gentle. The next section moves from close passages into deeper blending. When encounters repeat or become more direct, disks can be scrambled into smoother forms, and the difference between spirals and ellipticals can become a history written in light. A galaxy can lose its neat disk without losing its light. A merger scrambles, orbits and smooth shapes often nudging a spiral toward an elliptical form. At this distance, two galaxies overlap in a slow, uneven glow. Their centers remain distinct for a time. Between them, dust forms twisted lanes. The lanes cross at odd angles. They look like dark stitches pulled tight then loosened. The physical detail is in the crossing shadows. Where two lanes overlap, the darkness deepens. Where a lane bends, the edge becomes ragged like torn cloth. The first small unlock arrives early. A merger changes a galaxy by mixing motions, not by erasing stars. The scene drifts closer to the region between the two bright cores. The starlight there is brighter than either disk would produce alone. It is a bridge of blended light and gas. In that region, gas clouds collide more often. Collisions compress gas. Compression can trigger bursts of star formation in dense pockets. This is the first core concept. The second is orbit mixing, where stellar paths tilt and cross until a disk no longer dominates. The third is relaxation, the gradual settling into a new smooth profile after the strong interaction. The everyday analogy is calm and unique. It resembles two slow streams of milk meeting in a bowl of tea. The boundary between them becomes marbled, then the marbling fades as the fluids mix. The galaxy's stars are not fluids, but the visual blending captures the sense of redistribution. Another slow visual anchor appears along the outer edge. A faint arc wraps around the pair like a thin shell. The arc is subtle. It is brighter along one curve, then fades. Its boundary is soft. It is not a sharp ring. It looks like a whisper of light tracing an old wave. This shell can form as stars fling outward and then fall back along new paths. The arc is a record of mixing in progress. Another small payoff settles. Smooth halos and shells can be leftovers of a disk that has been rearranged, not simply a sign of age. The view shifts to one galaxy's former spiral arm. The arm is still visible, but it is stretched and kinked. Its knots are smeared. The dust lane that once ran cleanly along the arm now splits and twists. Some parts of the lane fold inward. Some parts fan outward into diffuse haze. That change matters. It shows that the cold gas reservoir is no longer confined to a thin mid-plane. It is being thrown into different heights and angles. Without a steady plane, gas can heat and disperse. Yet during the active phase, gas can also pile into the center and ignite a strong burst. The scale shift becomes gentle and wide. A single dust knot might span a few hundred light years. The whole interacting system spans tens of thousands of light years. The forces that twist a knot are the same forces that draw out tidal tails and shells. The camera pulls back to reveal a long tidal tail. The tail is faint. It extends far beyond the overlapping disks. Along it, small beads appear again, but less regularly than before. The tail's edge frays into strands. The strands fade into darkness. A small payoff arrives. A merger can both create long tails and build around a core at the same time because different regions respond differently to the same encounter. Now the focus returns inward. The two cores draw closer. Their surrounding light becomes more continuous. The separate disks become harder to distinguish. The combined glow grows rounder. The brightness profile becomes smoother. The center becomes denser. The outer halo becomes more extended. This is orbit mixing made visible as shape change. Stars that once moved mostly in a plane now occupy many inclinations. Their paths cross. Their collective light becomes a smooth oval haze. Another visual anchor appears in the central region. A bright inner glow is wrapped by a faint lopsided envelope. The envelope has a gradient that steepens toward the center. It looks like a cushion with a deeper indentation near the middle. This indentation suggests mass concentration. It can be built by gas inflow during the merger. Inflow feeds central star formation. It can also build a thicker inner component. Another small unlock settles. A merger can make a galaxy look older by smoothing it, even if it briefly forms many new stars during the process. A calm number anchors the timescale of the dramatic phase. The strongest visible distortions can last about a few 100 million years. That span is like the time it takes for a coral reef to grow from sparse patches into a broad structure. In a galaxy's life, it is a short chapter, yet it is long enough to reassign orbits and move gas across large distances. After the strongest phase, relaxation continues for longer. The halo can keep rearranging subtly. Shells can persist as faint arcs. The system gradually approaches a smoother equilibrium. Now a limit of observation enters softly and specifically. Mergers are not always obvious. If the encounter is viewed long after the strongest distortions fade, the remnant can look like a normal elliptical. Faint shells and tails can be below detection in shallow imaging. Projection can hide asymmetries. Two cores can overlap along the line of sight and appear as one. Models infer merger history from subtle features and from stellar populations. Those inferences depend on assumptions about how quickly features fade. They also depend on resolution. At great distance, a complex merger can compress into a single smooth blob. The limit is surface brightness sensitivity and time ambiguity. A signal would carry the present light but not the full path that produced it. Another slow scene returns to the faint shell arc in the halo. The arc is seen edge on. Its brightness peaks along a narrow curve. It fades away on both sides. This reveals the arc as a thin over-density. It is a boundary where many stars happen to gather along similar orbital phases. The arc is not a solid wall. It is a momentary crowding in a vast quiet space. Another small payoff lands. Even in a smooth-looking remnant, faint edges can trace the memory of mixing. The view pulls back to the final combined form. The two original spirals are no longer distinct. The remnant is rounder. The dust lanes are fewer. The light is smoother and warmer. The halo extends farther than the bright center suggests. The story now points forward without tension. The next section turns toward the quiet end state when star formation slows and a galaxy becomes quenched. The mechanisms of that quieting begin with fuel heat and the difficulty of cooling gas back into dense clouds. A galaxy can keep its stars and still lose its ability to make new ones. Quenching happens when cold gas becomes scarce or hard to cool, so star formation slows into a quiet trickle. At this distance, the first view is a smooth reddish oval glow. No dark dust seams cross the center. The outer light fades gently into the background. The physical detail is in that fade. The brightness falls outward in a steady gradient with no sharp edge where a disk would end. The absence of lanes is not proof of emptiness. It is a hint that the usual thin reservoir is missing or hidden in a different state. A first small unlock arrives early. Quenching is often a change of fuel and temperature, not a sudden removal of stars. The drift moves closer to the oval glow. The core is bright. The light is dense and uniform. Farther out, the texture becomes faintly grainy. That graininess is the blended shimmer of many old stars. The color tone is warmer than a typical star-forming spiral. Warm tone suggests older stellar populations dominate. Yet color alone can mislead. Dust can redden light. Distance can blur blue knots into the background. The story stays calm and precise. Quenching is a slowing of star formation rate. It is a shift from frequent new star birth to rare new star birth. The section holds to 3 core ideas. The first is starvation when a galaxy stops receiving fresh cold gas. The second is heating when gas is kept too warm to clump. The third is consumption when existing cold gas is used up faster than it is replaced. An everyday analogy stays gentle and unique. It resembles a hearth that still glows with embers after the last log is gone. Light remains, warmth remains. New flames do not rise because fresh fuel is absent. In a galaxy, the embers are old stars. The new logs are cold gas clouds. The drift shifts to a spiral galaxy that is beginning to quiet. Its disk is still visible, its arms still curve, yet the arms look smoother than before. Dust lanes are thinner, bright knots are fewer. The interarm regions are more uniform. This is a visual anchor of transition. The disk's edges remain, but the texture changes. The physical detail is in the dust lane contrast. Where a star-forming spiral shows deep shadows, this quieter spiral shows only shallow shading. That shallower shading suggests lower column density of dust and gas in the midplane. Another small payoff settles. A spiral can keep its shape long after its star formation rate has dropped because shape and fuel are not the same thing. Now the view follows a faint diffuse glow above the disk plane. It is not a sharp halo, it is a soft envelope. This envelope can be hot gas. Hot gas fills volume. It does not settle into a thin layer easily. When gas is hot and thin, it cools slowly. Cooling is the pathway back to dense clouds. If cooling is slow, collapse is rare. The scale shift becomes calm. A single cloud is a local object. Hot gas envelopes can fill tens of thousands of light years around a galaxy. The same matter can be a cloud when cold and a halo when hot. The state changes the future. Another small unlock arrives. Quenching can be a change of state, not a change of amount because gas can remain present but unusable. A single number anchors the pace of decline. A galaxy can use up its cold gas in about a few billion years if it forms stars steadily and receives little new fuel. That span is like the time it takes for a deep canyon to be carved by a persistent river. It is slow on a human sense. It is moderate on a galactic sense. Over that span, the brightest young stars come and go many times. Their signals fade quickly when the supply weakens. The drift returns to the oval galaxy again. Its smooth light suggests orbit mixing and an old dominant population. Yet quenching does not require a merger every time. Quenching can also occur in a disk that simply starves. Fresh gas can stop arriving. Gas already inside can be heated by gentle processes. Gas can be stripped in dense environments. The main effect is the same. Cold clumps become rare. Dust lanes fade. The visible signs of youth diminish. Another slow, visual anchor appears in the central region of the oval. The core has a brighter inner zone and a slightly less bright outer zone. The boundary between them is not sharp. It is a mild change in slope. This slope change can reflect how stars are distributed after long evolution. It can also reflect a past burst that built a denser center. Another small payoff lands. The shape of the light profile can hint at past growth even when no arms remain. Now a limit of observation enters softly and specifically. Quenching is inferred from light and from indirect gas traces. Dust can hide faint star formation. Old stars can overwhelm weak young signals. A small amount of new star birth can be missed if it is localized and the image is shallow. In addition, measuring gas state is difficult. Cold gas can be invisible in ordinary light. Hot gas can be invisible in ordinary light. Each requires different bands to trace. When those bands are unavailable, models fill the gap. Those models assume star formation histories. If the assumed history is wrong, the inferred quenching time is wrong. The limit is degeneracy. Different combinations of age dust and low-level star formation can look similar. A signal would carry the blended result, not the separate components. The scene returns to the quiet spiral once more. The arms are now faint. The dust seams are thin threads. The disk looks like a pale wash of light with gentle curvature. This is not a dead object. It is a system still rotating. It still contains matter. It still changes slowly. The change is simply less visible in newborn light. Another small unlock settles. Quenching is a shift in what dominates the glow from brief bright youth to long steady age. The transition forward is soft and steady. The next section moves toward one possible contributor to heating and quenching near the center, where a compact massive object can influence the surrounding gas. The tone remains calm. The path simply narrows from global quieting to central regulation. The brightest center of a galaxy can influence the faintest gas far around it. Central activity can heat and disturb gas-making cooling harder, and star formation less likely. At this distance, the galaxy is seen as a calm oval glow with a slightly brighter nucleus. Around the nucleus lies a soft haze that is not perfectly symmetric. One side looks a little more extended. The physical detail is in that uneven edge. The haze has a shallow gradient that fades outward. It suggests a region where gas and light interact. The first small unlock arrives early. A compact central engine can regulate a galaxy by changing gas conditions, not by removing starlight. The scene drifts closer to the nucleus. The core brightens. The surrounding haze becomes clearer. Faint filaments appear like wisps in a dim fog. The filaments are subtle. They arc outward and then dissolve. In that region, a supermassive black hole is the central object whose gravity dominates very near the core. It is not seen directly. Its presence is inferred from motions and from concentrated light. The section holds to three core ideas. The first is accretion, the process of gas falling inward and releasing energy. The second is feedback energy and momentum returning to the surrounding gas. The third is cooling balance, the struggle between gas losing heat and gas being reheated. Accretion is gas settling inward and releasing energy. The example is a bright nucleus and surrounding energized gas. The why is calm and direct. Released energy can warm or push gas, reducing future star formation. The everyday analogy stays gentle and unique. It resembles a kettle placed near a cold window. The kettle warms the air close by. The window still radiates cold. Between them, air currents form and reshape where condensation appears. In the galaxy, the nucleus is the kettle. The outer space is the cold sink. Gas responds by changing where it can cool and collect. Another slow visual anchor appears around the nucleus. A pair of faint lobes extends in opposite directions. The lobes are not sharp cones. They are soft plumes with rounded ends. Their edges fade in a long gradient. Between the lobes, the central region looks slightly darker, as if a thin veil lies across it. The veil can be dust mixed with gas. The lobes suggest outflow. Outflow is gas moving outward from the center, after being energized. The outflow does not need to be continuous. It can be episodic. It can be clumpy. It can carve cavities in surrounding hot gas. Cavities are low-density regions where emission is weaker. The physical detail sits in the cavity rim. A faint bright edge can outline a hollow like a bubble wall seen in dim light. Another small payoff settles. If energy inflates cavities, gas can be kept from settling into dense cold clouds near the center. The view shifts outward to the inner few thousand light-years. The galaxy's light profile remains smooth, yet faint ripples in brightness appear as arcs. The arcs are subtle. They mark where gas and stars have been gently disturbed. In that region, hot gas can fill volume. It can cool by radiating energy away. If it cools enough, it can condense into colder clouds that may form stars. Feedback can counteract this by reheating the gas or stirring it so it stays diffuse. The balance is delicate. A small change in heating can prevent a large amount of cooling over long time. The scale shift becomes calm. A cavity might span a few thousand light-years. The galaxy's halo can extend tens of thousands. A small core event can influence a vast volume, because gas is connected by pressure and motion. One number anchors the sense of size. A central region of influence can extend about 10,000 light-years, That span is like crossing a city-sized area again and again, then realizing it is only the inner zone of a much larger system. The comparison is about relative scale. The influence is large compared with the nucleus. It is still small compared with the full halo. Another visual anchor appears in the hot halo as a faint, smooth glow around the galaxy. The halo is not sharply bounded. Its emission falls outward in a gentle gradient. Within it, a darker patch suggests a cavity. Along the cavity edge, a thin, brighter rim appears. The rim is a physical boundary where gas is compressed. Compression raises density. Higher density can raise emission in some bands. Yet this does not necessarily lead to cold clouds. The gas can be compressed and still remain hot. Another small unlock arrives. Compression in hot gas can brighten a rim while still keeping the fuel too warm to collapse into stars. Now a limit of intuition and observation enters clearly. Central feedback is inferred from indirect signs. The outflow lobes can be faint and projection dependent. A lobe seen along the line of sight can look like a round glow. Cavities in hot gas can be missed without deep imaging in the right bands. Gas motions are measured through subtle spectral shifts. Resolution limits can blend different components into one. Models of feedback depend on assumptions about how often the nucleus is active and how energy couples to gas. Different coupling efficiencies can produce similar present-day appearances. The limit is that the central engine is not watched continuously. It is reconstructed from snapshots. A signal would carry the integrated light and the integrated gas emission, not the full sequence of episodes. The scene returns to the nucleus again. The bright core is steady in the frame. The surrounding haze has a slightly ragged edge. That raggedness suggests clumps. Clumps can be gas clouds being pushed or heated. Some clumps can survive and fall back. Some can disperse. The result is regulation, not a simple on and off switch. Star formation can be reduced without being erased. Another small payoff settles. Central feedback can act like a thermostat. It prevents runaway cooling, keeping the system near a quiet equilibrium. The view drifts outward to include the inner disk or inner bulge. Dust lanes are faint or absent. The light is smooth. This smoothness supports the idea that cold gas is scarce or confined to small pockets. Yet the outer regions may still hold some cold gas in a thin layer, especially in a disk galaxy. The central engine can quiet the core while leaving outskirts less affected. That uneven effect matters for galaxy evolution. It can build a red center with a slightly bluer edge. It can create gradients in age and color. The transition forward stays soft. The next section moves away from the central engine and toward environment, where a galaxy traveling through a dense cluster can have gas stripped and reshaped from the outside. The story remains calm. The focus widens from inner regulation to external pressure. A galaxy can be quieted from the outside while its inner light stays smooth and steady. In dense clusters, external pressure can strip a galaxy's gas and thin its star-forming layer. At this distance, a spiral galaxy sits inside a wide field of faint companions. The spiral's disk is slightly lopsided. On one side, the disk edge is crisp. On the other side, a faint plume extends outward like a soft smear. The physical detail is in the plume's boundary. It has a brighter rim that fades into a long gradient. This rim suggests a front where gas is being pushed and shaped. A first small unlock arrives early. Environment can remove fuel without destroying the spiral stellar disk at once. The scene drifts closer to the spiral. Dust lanes remain visible near the center. They are thinner than in a rich star-forming disk. The outer arms look pale and smooth. In the direction of the plume, the arms appear truncated. Their brightness drops more suddenly with radius. The truncation is a boundary. It marks where the cold gas layer ends more sharply than the starlight does. This section holds to three core ideas. The first is ram pressure, the force felt by gas moving through a thin hot medium. The second is stripping the removal of gas from the disk. The third is outside in quenching, where star formation fades first in outer regions. Ram pressure is a push on gas from surrounding hot plasma. The example is a one-sided gas tail and a truncated disk. The Y is calm and clear. If gas is pushed out, new stars become harder to form in the outer disk. An everyday analogy stays gentle and unique. It resembles a soft candle flame in a steady breeze. The wax body remains, the flame narrows and leans, the smoke and heat trail downstream. In the galaxy, the wax body is the stellar disk. The flame is the cold gas layer. The breeze is the cluster medium. Another slow visual anchor appears along the leading edge of the disk. A faint arc of brightness hugs the outer rim. It looks like a thin, bow-shaped glow. Behind it, the disk looks slightly dimmer. This bow-shaped arc is a compressed front. Gas piles up there. Density rises. In some cases, that compression can briefly enhance star formation at the edge. It can create a narrow band of young regions. Yet the same push that compresses can also remove. Gas that is not tightly bound is swept away. A small payoff settles. The same external pressure can both trigger a thin edge of activity and erase the broader reservoir behind it. The drift follows the plume outward. The plume is not uniform. It breaks into clumps. Each clump has a brighter head and a fainter tail. The heads are rounded. The tails taper. This head and tail shape suggests motion through a medium. Gas is being stripped in pieces. The pieces are stretched. They mix with surrounding hot material. The physical detail is in the clump edges. Some edges are sharp. Some dissolve into haze. Sharp edges suggest a denser core. Dissolving edges suggest mixing and heating. The scale shift becomes gentle. A single clump can be a few hundred light years across. The full tail can extend tens of thousands of light years. That tail length matters. It shows that gas can be removed far beyond the visible disk. It also shows that the loss is not confined to the immediate edge. Another small unlock arrives. Stripping can carry away the future because removed gas is no longer available to cool back into the disk quickly. The view returns to the disk itself. The inner regions still show dust seams. They curve along inner arms. The seams look thinner but remain coherent. The outer disk, however, is smoother and redder. The difference across radius is the signature of outside in change. Young stars fade first where gas is removed first. The inner disk can continue forming stars for a time if gas remains bound there. Over time, even the inner reservoir can be reduced either by ongoing stripping, by starvation of new inflow, or by heating. A single number anchors the duration of visible transformation. Outside in quenching can progress over about 1 billion years in a cluster environment. That span is like the time it takes for a shoreline to retreat a long distance under persistent waves. It is not a single storm, it is a steady pressure. In that long span, the outer disk can change from patchy and blue to smooth and faint. Another visual anchor appears as a sharp cut-off in the outer dust lanes. The lanes simply stop beyond a certain radius. Starlight continues, but the dark seams vanish. This is a physical boundary of fuel. It indicates that dust and cold gas are missing there. The boundary can be slightly curved, matching the disk. It can also be uneven, depending on direction of motion. Another payoff settles. A galaxy can look like a normal spiral in starlight while its gas disk has already been trimmed. Now a limit of observation enters softly and specifically. Stripping is easier to see in gas-sensitive bands than in ordinary light. In visible images, tails can be too faint. The bow front can be subtle. Projection can hide the direction of motion. A tail aligned along the line of sight can look like a mild haze, not a stream. In addition, the hot cluster medium is mostly invisible in ordinary light. Its density and pressure must be inferred from other signals. Without those, the strength of ram pressure is uncertain. The limit is multi-band dependence and geometry. A signal would carry only the brightness distribution, not the full three-dimensional flow. The scene returns to the wider cluster field. Many galaxies appear close in projection. Some are smooth ovals, some are faint disks. The environment is not the same everywhere. Near the cluster center, the medium can be denser. Farther out, stripping is weaker. That creates a gradient of galaxy types. Spirals become rarer toward the core. Smooth red systems become more common. Another small unlock settles. Environment can sculpt a population, not only individual galaxies, by shifting how many keep their gas. The transition forward is gentle. The next section moves from external pressure into long-time consequences, where repeated quieting and mixing build the present-day diversity of galaxies. The view widens. The story shifts from single events to the slow arc of cosmic time. A galaxy's present shape is a snapshot taken from a very long story. The mix of spirals and ellipticals reflects how often gas arrives, how often interactions occur, and how long quiet phases last. At this distance, the scene widens into a loose tapestry of many galaxies. Some are thin disks with faint arms, some are smooth ovals with soft edges. Between them is darkness that is not empty. It holds thin gas and faint light that does not belong to any single galaxy. The physical detail is in the halos. Around several ovals, the outer light fades in a slow gradient. Around several disks, the outer edge is sharper. The difference in edge sharpness hints at different orbital structures inside. A first small unlock arrives early. A spiral or an elliptical is less a category than a record of how motion and fuel have been managed. The drift moves toward a region where a spiral and an elliptical sit near each other. The spiral shows a thin midplane and faint dust seams. The elliptical shows a rounder glow with little internal contrast. The two are not opposites in every sense. Both contain stars. Both contain dark matter halos. Both are shaped by gravity. The difference often lies in cold gas and in orbital order. This section holds to three core ideas. The first is assembly history, the sequence of growth events. The second is angular momentum, the ordered spin that supports disks. The third is morphological transformation, the slow shift of shape when events disrupt that order. Angular momentum is the tendency of rotating matter to keep a disk. The example is a spiral's thin plane and ordered rotation. The Y is calm and direct. If ordered spin remains, disks persist, and star formation can continue where gas is cold. The everyday analogy stays gentle and unique. It resembles a potter's wheel that keeps clay spread into a flat disk when it spins steadily. If the wheel is jolted repeatedly, the clay slumps into a thicker mound. In galaxies, the wheel is ordered rotation. The jolts are mergers and tides. Another slow visual anchor appears in a thin spiral disk seen slightly tilted. The disk has a bright midplane and a faint thick component above and below. Dust lanes trace along the midplane like soft shadows. The shadows are darker near the inner region. They become thinner outward. This layered look is a physical clue. It suggests a cold, thin layer embedded in a warmer, thicker population. That layering helps preserve spiral structure. It also provides a place where clouds can form. Another small payoff settles. A spiral can be understood as a layered system where the thin layer carries most star formation, even when the thick layer dominates mass. The view shifts to a nearby elliptical. Its light is smooth. It shows subtle contours like faint nested ovals. No dust seams cut across it. The edge is not sharp. It fades gently into the background. This smoothness is a physical clue of orbit mixing. Stars move on many inclinations. Their paths overlap in a near spherical distribution. Without a thin plane, cold gas has fewer stable places to settle. If gas is present, it can be heated or swept. The elliptical's calm appearance can therefore align with low star formation. Another small unlock appears. An elliptical does not need to be built in one dramatic event. It can be assembled through many smaller interactions that gradually thicken and mix the disk. The scale shift becomes gentle and wide. A single star orbit is tiny compared with the galaxy. Yet the statistics of many orbits shape the entire light profile. Over billions of years, small perturbations add up. A minor merger can tilt a disk slightly. Repeated minor mergers can thicken it. Gas accretion from the surrounding medium can rebuild a thin layer if conditions allow. The same halo can host different visible forms at different times. One number anchors the long arc, Much of a large galaxy's assembly occurs over about 10 billion years. That span is like the time it takes for a mountain range to rise and then be worn down into rounded hills. In that long interval, disks can form, be disturbed, and sometimes reform. Ellipticals can grow by adding stars from smaller companions. Spirals can grow by adding gas and turning it into new stars. Another visual anchor appears as a faint stream of starlight between galaxies. The stream is a thin ribbon. It is barely brighter than the background. It curves like a loose arc. This is a tidal stream. It is a remnant of a smaller companion being dissolved. Streams contribute to halos. They add stars to the outer regions. Over time, many streams overlap and become a smooth halo glow. Another small payoff settles. Smooth halos can be the blended memory of many faint streams even when no single stream remains obvious. Now a limit of observation enters softly and specifically. Classifying galaxies by shape depends on image depth and resolution. A distant spiral can appear smooth and be misclassified as an elliptical. Faint arms can vanish in blur. Dust can hide structure. In addition, the same galaxy can look different in different wavelengths because young stars, old stars, and dust trace different parts. Assembly history is inferred from present structure and from stellar populations. Those inferences depend on models of star formation and dust. Different histories can produce similar colours and profiles. The limit is that the long time sequence is reconstructed from snapshots and probabilities. A signal would carry only the current light distribution, not a full timeline of past interactions. The scene returns to the wide tapestry. Disks and ovals share the same space. The distribution is not uniform. In denser regions, smooth ovals become more common. In quieter regions, disks persist more often. This pattern reflects both environment and chance. It also reflects that gas supply and interactions are not evenly distributed. Another small unlock settles. Galaxy evolution is not a single track. It is a set of paths that depend on how often fuel arrives and how often order is disturbed. The transition forward remains soft. The next section moves from shapes and histories toward the faint light between galaxies, the diffuse glow that accumulates from stripped stars and scattered material. That diffuse light widens the perspective from individual galaxies to the spaces that connect them. Between galaxies, a faint glow collects like a quiet fog. This diffuse light is built from stars and dust that are pulled away during interactions and stripping. At this distance, the scene is not centered on any single galaxy. A broad region of space holds a soft, uneven sheen. It is brighter near a cluster core. It fades outward in a gentle gradient. The physical detail is in the texture of that sheen. It is not smooth like a single halo. It has mottled patches and thin threads. Some threads curve in long arcs. Some patches look like barely lit clouds. A first small unlock arrives early. The space between galaxies is not empty of stars, and those stars can reveal past encounters. The drift moves closer to a thin arc of light. The arc is long and narrow. Its edge is sharper on one side. On the other side, it dissolves into faint haze. The arc looks like a ribbon torn from a larger fabric. Its curvature suggests it follows an orbit around the cluster center. This section holds to three core ideas. The first is tidal stripping stars pulled away by gravity during close passages. The second is intra-cluster light, the diffuse population of unbound or loosely bound stars in a cluster. The third is phase mixing, the slow blending of streams into a smooth background. Intra-cluster light is starlight not bound to one galaxy. The example is the faint sheen filling the cluster space. The Y is calm and direct. This light records how often galaxies have interacted and how material has been redistributed. An everyday analogy stays gentle and unique. It resembles dust motes in a sunbeam inside a quiet room. The room feels empty at first. Then the beam reveals drifting particles. In the cluster, the beam is deep imaging. The dust motes are faint stars spread through the space. Another slow visual anchor appears near the outer envelope of a bright elliptical galaxy. A very faint shell wraps around it. The shell is offset. It forms a partial arc rather than a full ring. Along the arc, brightness peaks and then fades. The boundary is soft. The shell hints at a past encounter where stars were lifted into new orbits. Over time, those stars drift and spread. The shell becomes fainter. It contributes to the wider intracluster glow. Another small payoff settles. Features that look like delicate ornaments can be the first stage of a much larger diffuse component. The scene shifts outward to a region where multiple thin streams overlap. Each stream has a slightly different curvature. Where they cross, the light thickens. Where they diverge, it becomes barely detectable. This is phase mixing in progress. Different orbital periods stretch the streams. Different inclinations spread them. Eventually, the streams smear into a smooth background. The physical detail is in the edges. A young stream has a crisper boundary. An older stream has a fuzzier boundary. The fuzziness is not just distance. It is real dispersion of the star paths. The scale shift becomes calm. A single star is a point of light. A stream is tens of thousands of light years long. The cluster itself spans millions of light years. The same gravitational field guides both the arc of a stream and the larger distribution of galaxies. Another small unlock arrives. The cluster's overall gravity writes a map in faint starlight, because stripped stars continue to orbit long after they leave their original galaxy. One number anchors the faintness in a safe way. Intracluster light can amount to about a few tens of % of the total starlight in a rich cluster. That proportion is like the foam on a long river. The foam is not the whole river, yet it covers large areas and shows where turbulence has been. In a cluster, the diffuse light is not the whole stellar mass, yet it spreads widely and marks where interactions have been common. Another visual anchor appears as a broad glow around the cluster core. It has no sharp edge. It fades outward in a slow gradient. Embedded within it are faint knots. The knots are not bright enough to be galaxies. They are over-densities of this diffuse component. Some may be the debris of small systems that were dissolved. Some may be temporary crowding along orbital paths. Another small payoff settles. The diffuse glow can carry substructure, meaning the cluster is still being assembled rather than fully settled. Now a limit of observation enters softly and specifically. Diffuse light is hard to measure because it sits near the background level. Small errors in subtracting foreground stars or in calibrating sky brightness can erase or invent faint features. The measured amount of intracluster light depends on how deep the imaging goes. It also depends on where the boundary between a galaxy's halo and the diffuse component is drawn. That boundary is not sharp. It is a gradient, and models must choose a definition. In addition, streams can be hidden if they lie behind brighter halos in projection. The limit is surface brightness sensitivity and definition ambiguity. A signal would carry only the combined glow, not a labelled separation of what belongs to which component. The scene returns to a single long stream again. Along its length, brightness varies gently. It is brighter near one end. It fades toward the other. This gradient suggests the stream is connected to a more massive remnant at one end. Yet the remnant may now be dim and compact. The stream outlives the clear identity of its source. Another small unlock settles. Debris can persist as a shape longer than the source system remains recognizable. The view widens once more to include several galaxies embedded in the diffuse light. The galaxies appear like islands in a pale sea. The sea is made of old stars and scattered material. This sea grows with time as interactions accumulate. It becomes a quiet background that holds the history of a region. The transition forward stays soft. The next section moves from diffuse light in clusters to the broader cosmic timeline where the overall star formation rate of the universe rises and falls. The focus shifts from local debris to the long rhythm of cosmic history. Across the universe, star formation rises, peaks, and then slowly fades. That broad rhythm is set by how gas cools, how it is replenished, and how it is prevented from settling. At this distance, the scene is no longer a single galaxy or cluster, It is a layered field of many faint galaxies at many distances. Some are tiny smudges, some are thin streaks. Their light is dim and redshifted, stretched by expansion as it travels. The physical detail is in the collective texture. The sky is not uniform. It contains a gentle gradient of faint sources, denser in some regions, sparser in others. A first small unlock arrives early. The universe forms stars most actively when gas supply is rich and cooling is efficient. Then the activity declines as conditions change. The drift settles on a sequence of galaxies arranged in depth. Nearby ones show clearer shapes. Distant ones are smaller and softer. The more distant the galaxy, the less of its structure is resolved. Yet a pattern emerges. Some distant systems appear clumpy. Their light breaks into knotty patches. The knots are compact and uneven. The surrounding light is faint. This clumpiness suggests vigorous star formation regions embedded in gas-rich disks or irregular shapes. Other galaxies appear smooth even at modest distance. Their light profiles are rounder. Their edges fade gently. This section holds to three core ideas. The first is cosmic star formation history, the changing global rate of star birth. The second is gas accretion, the supply of fresh gas from surrounding space into halos. The third is quenching processes that reduce star formation by removing or heating gas. Cosmic star formation history is the global pace of star birth over time. The example is a universe that looks clumpier and bluer at earlier epochs. The why is calm and direct. The peak and decline explain why many galaxies today are quieter and redder. An everyday analogy stays gentle and unique. It resembles a garden after a heavy seasonal rain. After the rain, growth is vigorous and widespread. As the season dries, growth continues in pockets, then becomes sparse and slow. In the universe, the rain is abundant cold gas supply. The drying is the gradual difficulty of cooling and replenishment. Another slow visual anchor appears as a distant galaxy, with several bright knots along a rough arc. The knots are not evenly spaced. Each knot has a slightly diffuse edge. Between knots, the light dips. The arc is not a perfect spiral. It is a disturbed disk or a forming structure. The physical detail is in the knot edges. Their brightness gradients suggest dense regions surrounded by thinner gas. In that region, gas can cool and collapse into clouds. Those clouds form clusters of young stars. Over time, these clusters disperse into a smoother background. Another small payoff settles. Clumpiness can be a sign of youth and high gas fraction, not simply a lack of order. The scene widens again to include many galaxies at intermediate distances. The average appearance shifts. Disks still exist. Smooth ovals appear more often at later times. The global environment changes as the universe expands. Gas in halos can be shock-heated to high temperatures in massive systems. Cooling becomes harder. In smaller systems, gas can still cool but may be lost more easily through winds and stripping. In both cases, the global star formation rate trends downward. The scale shift becomes gentle. In a single cloud collapse occurs over millions of years. In a galaxy, star formation patterns shift over billions. Across the universe, the rise and fall unfolds over much of cosmic time. One number anchors the broad peak in a safe way. The global star formation rate peaks roughly 10 billion years ago. That timing is like a long-ago high tide after which the sea gradually retreats. It does not vanish at once. It leaves behind wet channels and pools where activity continues. In the universe, those pools are gas-rich galaxies that keep forming stars later than average. Another visual anchor appears in a nearby galaxy with a faint outer disk and a brighter inner region. The outer disk is smooth and pale. The inner region shows a few dust lanes and a mild brightness concentration. This contrast suggests inside regions may keep star formation longer, while outskirts fade. It reflects both internal regulation and external effects. Another small payoff settles. The decline in global star formation is not a uniform dimming. It is a patchwork with some regions and galaxies quieting earlier than others. Now a limit of observation enters softly and specifically. Measuring cosmic star formation history requires converting light into star formation rates. Dust can hide young stars. Different wavelengths trace different timescales. At large distances, only the brightest galaxies are seen, which biases samples. Small galaxies can be missed entirely. In addition, distance estimates depend on redshift measurements. Uncertainty in redshift can blur the timeline. The limit is that the global curve is reconstructed from incomplete and biased views. A signal would carry stretched light and integrated brightness, not a direct count of newborn stars. Models must correct for what is hidden and what is missed. The scene returns to the clumpy distant systems. Their knots appear intense, yet they are small. Some will merge into larger structures. Some will be quenched early. Some will settle into disks. The same physical processes repeat at different scales. Gas accretion feeds. Feedback and environment regulate. Gravity shapes orbits. Over time, the universe shifts from a high-activity era to a quieter one. Another small unlock settles. The peak is not a single cause. It is the moment when supply, cooling, and regulation align most strongly across many systems. The transition forward remains soft. The next section resolves gently by returning to the close-up view of galaxy forms now understood as outcomes of a long rhythm. The ending steadies and quiets. The view prepares to rest in the slow glow of mature galaxies. A galaxy's shape is a memory held in light and motion. That memory settles into spirals, into smooth ellipses, and into the quiet in between. At this distance, evolution is not a story of one event. It is a slow sorting of gas stars and gravity across time. The view begins with a mature spiral seen nearly face-on. Its disk is thin. Dust lanes trace gentle curves. The arms are not razor-sharp. They fade and reappear like soft brushstrokes laid on a darker canvas. In the centre, a mild bulge rises. Its brightness increases smoothly toward the core. The physical detail rests in the gradients. The disk has a clear edge where light falls away. The bulge has a rounder, steadier profile. A first small unlock arrives early. Spirals and ellipticals are not separate species. They are outcomes of how gas stays available or becomes unavailable for long periods. The scene drifts along the spiral's disk. A few pale, star-forming regions sit along one arm. They are not blazing. They are modest knots with diffuse boundaries. Between them the arm is made of older starlight. The disk looks layered. A thin dust lane lies slightly offset from the brightest band. That offset hints at gas responding to the spiral pattern. The section holds to three core ideas. The first is morphological transformation, the gradual change of galaxy shape. The second is gas exhaustion, the decline of star formation as gas is consumed or removed. The third is dynamical heating, the process that thickens disks and randomizes stellar orbits. Morphological transformation is a change in a galaxy's visible structure. The example is a spiral disk that becomes thicker and smoother after repeated disturbances. The why is calm and direct. Shape is a clue to how stars move and how gas has been treated. An everyday analogy stays gentle and unique. It resembles a well-worn path through grass. When the ground stays soft and damp, footprints keep forming and the path remains defined. When the ground dries and hardens, footprints stop marking clearly, and the path slowly fades into a uniform field. In a spiral, gas acts like the soft ground. It keeps patterns vivid through new star formation. When gas becomes scarce, the visible pattern fades towards smoothness. A second visual anchor arrives. The view shifts to a large elliptical galaxy. Its light is smooth and round. It has no arms. It has no dust lanes. Its brightness declines steadily outward like a quiet dome. At the edge, the light becomes so faint it merges into the background. The physical detail is in the isophotes, the nested contours of equal brightness. They are nearly concentric, yet there is a slight flattening. It suggests the galaxy is not a perfect sphere. The stars inside move on many different orbits. Some are elongated, some are tilted. The combined result is a calm, even glow. Another small payoff settles. A smooth appearance often means stellar orbits are randomized enough that no thin disk remains dominant. The drift moves to an intermediate case. A galaxy with a disk exists, but it is thick. The arms are faint. The disk edge is less crisp. The central bulge is more prominent. The outer regions are smoother than a young spiral. This is where dynamical heating becomes visible. Small mergers and repeated tidal encounters puff up the disk. Stars that once orbit in a thin plane gain vertical motion. The disk becomes thicker. The arms become less contrasty. Gas can still exist, but it may be less able to gather into dense lanes. Another small unlock arrives. Even without a dramatic collision, repeated mild disturbances can shift a galaxy's appearance over billions of years. One number anchors the long perspective in a safe way. The universe is about 14 billion years old. That span is like a library with 14 long shelves. Each shelf holds a billion years of gradual changes. A single spiral arm pattern lives only on a few pages of one shelf, yet the library's total arrangement determines which shapes become common at later shelves. The scale shift stays gentle. A star cluster disperses over tens of millions of years. A disk thickens over billions. A galaxy population changes over most of cosmic time. Another visual anchor appears in a quiet group environment. Several galaxies sit near one another. A faint bridge of light connects two of them. The bridge is narrow. Its edges feather into darkness. A subtle twist runs along it. This bridge is not bright enough to dominate the scene. It is a whisper of interaction. Nearby, one galaxy's outer disk shows a slight warp. The disk plane bends gently like a soft sheet lifted at one corner. The physical detail is in that warp. It suggests the gravitational field is not perfectly symmetric. Over time, such asymmetries can heat disks and redistribute gas. Another small payoff settles. Transformation often begins at the outskirts. The outer disk is the first to warp, to lose gas and to fade. Now a limit of intuition and observation enters softly and specifically. It is hard to reconstruct a single galaxy's full history from one snapshot. Different evolutionary paths can lead to similar present-day shapes. A thick disk can come from many small encounters or from internal instabilities. A smooth elliptical can come from a major merger or from repeated smaller mergers. Observations also face a resolution limit. At larger distances, fine structure is blurred. Faint tidal features sink below the detection threshold. In addition, dust can hide star-forming regions and make a galaxy appear smoother than it is. The limit is degeneracy of interpretation and incomplete visibility of faint features. A signal would carry integrated light, not the complete record of every interaction. Models must combine statistics across many galaxies to reduce ambiguity. The view returns to the first spiral. Its arms are calm, the dust lanes are soft. The star-forming knots are sparse. The galaxy feels settled. In that steadiness, the broader arc becomes clear. Gas supply sets the tempo. Environment shapes the edges. Gravity rearranges orbits. Star formation marks the present moment, then fades into older light. Another small unlock settles. Galaxy evolution is a balance between structure and supply. When supply is gentle and continuous, spirals can persist. When supply is disrupted or heated, smoothness grows. The closing transition remains quiet. The camera drifts outward until spiral and elliptical sit together as simple forms. Light behaves as a slow messenger across enormous distances. The scene stabilizes in a soft, even glow that holds no urgency. Rest comes naturally as the shapes remain, and the universe continues its calm rearrangement.